Dear students, last lecture we discussed about power electronics application, its range, and discussed UPS in detail. Now we are going towards next lecture in power electronics application. And in this lecture, we are going to discuss electronic ballast and induction. So let's start with it. So what we seen in the last lecture was power electronics application, online and offline UPS, single conversion, double conversion mode, UPS selection factors. As well, we discussed what power electronics is. Now, in this lecture, we are going to discuss electronic ballast, characteristics of fluorescent lamps, advantages of electronic ballast over conventional ballast, and part of the induction. In the next lecture, we are going to discuss DC drives, in particular, single phase DC drives. So let's turn towards today's contents. We're going to discuss electronic ballast. You've seen electronic ballasts. Almost everybody from you has seen this. These are basically converters used to supply the discharge lamps. Discharge lamps means, again, these are fluorescent lamps. And these fluorescent lamps are operated, this ballast supply them signal at several kilohertz of the frequency. This several kilohertz of the frequency ignites that lamps, as well as higher frequencies increases the lamp luminous efficacy, because the entire spectrum is not a useful spectrum. But to have only visible spectrum, some part of it is useful, and ballast has to concentrate over that part. So if that part is more, naturally the efficacy of luminous light intensity will be, light intensity and efficacy will be better. So what electronic ballasts do, or what are benefits after using ballast are, it increases efficacy as well as increases efficiency and the lamp life itself. Means lamp will run for longer luminous hours. Size. Now electronic ballasts are available in very small size, just few centimeters by few centimeters, and very small. But it has improved the lighting quality a lot. So first try and understand what the discharge lamps are. See, these are basically the discharge lamp or fluorescent tube. And let's understand how it works. These are two electrodes which are at ends. And these are the phases through which this lamp glows, and then we get light out of it. It is generation of heat, excitation of atom, ionization, and then radiation of the energy. This is how it goes through these three phases and gives us light. During the stabilization process, there is a breakdown phase and warm-up phase. Warm-up phase is initial phase, rather before discharge lamp glows fully. Means you can say that starting phase. Few discharge lamps are with capacitor-based starters also, and you don't need it at all. So if I check all discharge lamps, their wattages, their lives, and their lumen versus wattage, means efficacy, then these fluorescent tubes are available right from 4 watt to 100 watt with 20,000 hours life, means almost a year. considering we use these lamps for 6 hours or 7 hours a day. Whereas compact fluorescent, the small tubes with the better luminous efficacy can work for 10,000 hours. Sodium vapor lamps, low pressure lamps are available up to, low pressure are available up to 150 watts and high pressure are available up to 500 watts with better luminous efficacy and life. Mercury vapor lamps generating quite heat also. They are available up to 1000 watts, but luminous efficacy is not as good as the fluorescent lamps. And they give some, we can say, bright light, but a better life of the lamp. Halogens available up to 50,000 watt, generally used in big grounds or where functions or some big audience is expected. Luminous efficacy is 80 to 120, but life is not that. And HPS amalgam lamps are again low on efficacy and low on life also, but available in higher voltages up to 1 kilowatt. Then these discharge lamps are glowing with the help of ballast. Then what the ballast is? This is power line, a Siemens EMI filter. The first part in ballast is electromagnetic interference filter, means avoids the EMI, reduce EMI content, maybe radiated or conducted EMI from the power line, then converts this AC to DC using small control rectifier. This DC bus is again connected to inverter to convert it to high frequency. Means what we did till this point, we used AC source, converted it to first reduced EMI, converted it to DC, use this DC link to convert the same signal at a higher frequencies, naturally at a lower voltage. And these are controlled using a control mechanism like a base drive or a gate control in case of MOSFETs. And these high frequency signals are fed to the electrodes as it's seen through high frequency ballast. And these two are the electrodes. And in some cases, there is a capacitor starter which is required. So the blocks are EMI filter, which has two coupled inductors and a capacitors to attenuate the EMI. Full bridge converter with filter for DC converter. DC to AC inverter is giving high frequency AC signals to high frequency ballast, and this ballast is providing signal to lamp in order to glow the lamp through the phases condition. So in case starting voltages are higher, separate ignition circuit, means which gives very high energy pulse, is required, and usually a capacitor vessel. And to control the rectifier and inverter, we do have control and protection circuit for the lamp. This is how electronic ballast typically works. In these ballast, we do have either non-resonant ballast or resonant ballast. In case of non-resonant ballast, we remove the output diode of DC to DC converters, means in DC link, and small capacitors, split capacitor is used to ignite the lamp initially. See how it works. These are electrodes. This is capacitor which is used to ignite the lamp. This is the ballast circuit. And this is your DC link. If the output diodes are removed, then this will generate a high frequency signal here, and the flyback action will not take place. But the drawback is it generates a high voltage spike because this action of protection will not be there, and naturally high switching loss. So efficiency gets reduced because hard switching is always an undesirable phenomena because the switch undergoes higher stress of higher voltage and current at the same time. So it must be avoided as far as possible. So we turn to the resonant ballast. And these resonant ballasts are either voltage fade or the current fade. In current fade, we do have either push-pull or full bridge ballast. We can see one of the uh, bridge ballast over here, where this is DC link, a choke circuit, a full bridge circuit, a ballast, a capacitor starter, and provided to the discharge lamp, electrodes of the discharge lamp. This is a full bridge circuit where a transistor followed by a diode to this LC circuit forming a H type of a bridge in order to resonate this for the LC tank circuit. Then in order to design a ballast or to make a ballast, what parameters must be known or some cares has to be taken while designing or manufacturing a ballast are that all ballasts are operated at minimum frequency of 20K and up to 100K. Even in that, avoid around 40K frequency because it is used for some other communication purposes. Minimum 20K plus is for the purpose to avoid interference with audio or that sound, discharge sound must not be audible one. Lamp current must be ideally a sinusoidal one because we are using HF inverter and then passing it to ballast. Then if it's a quasi square wave or some irregular wave shapes, then one thing is switching losses will be increased as well as disturbances in discharge lamp means during glow of a discharge lamp may be observed. So all these waveforms must be with a crest factor less than 1.7. So energy distribution will be. For starting the lamp, warm up it up to 800 degrees centigrade. Means electrode has to be heated up to 800 degrees centigrade and apply minimum voltage to ignite so that lamp at this higher temperature, lamp will glow. And during dimming, start at max lighting level and then slowly reduce the output level. We should not start dimming initially because that discharge lamp has to glow fully first, and in order to glow it fully, you need a warm-up phase and a breakdown. If you start dimming, then breakdown may or may not occur and lamp will not glow itself, so there is no issue of dimming, or that dimming will not happen properly. There might be flickers observed. So glow it fully and then dim it as per your requirement. Then reduce the intensity. Selecting acoustic frequency in a range of free range of acoustic means either below 1 kilohertz or above 100 kilohertz. And above 100 kilohertz is more preferred. So the other methods of these starting and resonance are FM frequency modulation, square wave operations, and sine wave suppressed with third harmonics means 150 hertz frequency. These ballasts, as we discussed, are used in all portable lightings, discharge lamps, emergency lightings, fluorescent lamps, when automotive lightings and applications, home and industrial lighting, They provide low volume and size uh, in few centimeter by centimeter, as we discussed, and reduce the luminary size, means the overall size of the discharge lamp. Because before few years, a decade back, that electronic choke using inductor was a bulky one. Now it's reduced, just means electronic ballast is available just in 2 or 3 centimeter by 3 centimeter size, hardly. Means it is almost 10 to 15 times smaller than the inductive choke used in the fluorescent lamps. Though this is a small but wonderful and useful application of power electronics, and one can go for designing and manufacturing a ballast. Next application, which is heavily used at industrial level only, is induction. Means heat up metal, particularly MS or iron or ferrous materials, based on the principle of induction by using the skin effects, uh, calculating the skin depths, but not hitting it directly. So induction heating is based on supply of energy by means of electromagnetic induction inside the metal. It's applicable for metal. So what we do is we transfer energy using electromagnetics, and transformation of this electrical energy into heat due to Joule's effect, as we know, P is equal to S square R. So transmission of this heat inside this mass is by means of thermal conduction, because uh, energy is transferred by electromagnetic induction, and as we go deeper uh, in ability, suppose a cross section is a circle, and due to skin effect, electromagnetic radiations or electromagnetic field is generated outside of that particular cross section, means that particular solid iron bar, then the heat is penetrated in a depth using a thermal conduction, because that metal has to be heated fully up to a level of 1200 degrees centigrade, etc., if it's a forging application. So in order to make a induction heater, it must be a coil suitably wound and a good dimension. It needs a heavy coil, and it shall be around the metal parts, and the metal part will be passed from inside the coil. This coil must be wound around in some good chamber that it shall not be open. Again, this conducting at high frequency AC currents, and these induce on the workpiece. These induce, say, energy on the workpiece, means that metal object, uh, by the ED current methods. And this intensity control of these radiations is nothing but controlling the heating period of the metal. The most important part out of this is there is no physical contact between a metal object or the workpiece and the induction coil. So this involves only metal parts to be treated and characterized by high energy transfer without loss of heat, because metals are good conductors of heat. Based on these basic principles, we design and use the induction heaters, which are heavily used in the industries. So where these are used? There are variety of applications you can see. Can you identify something? First one is silver brazing, which is hard brazing. So metal is heated by induction effect, and it is getting brazed, if you can see this part. Second one is a tin soldering. This one, and this is a heat treatment. These names are the same. This is hardening and annealing. It's anneal the material, hardened it from outside, not from inside. Means control the skin depth, just anneal the material and send it for the next process. This is melting and heat it to a very high temperature up to 3000 degrees centigrade. And this is typical induction heaters used in forging and other spare. These bars are carried through these heaters, heated long, and then these are processed further. So in order to do this, you need induction heating generators, the big equipments. They consider the power unit first. Typical three elements, out of which first is the power unit. And this part is to take the mains frequency and increases it to up to 900 kilohertz. Means you have to use the switches, mostly the MOSFETs, which will withstand this frequency and very high current. The induction heating currents are very high because this is a high power application and power output is up to 400 kilowatts. Remember, whether to hit a metal piece, which do have these melting points around 3000 plus degrees centigrade. So hit them up to the core needs a lot of power. Next part is a workhead, where actual coil is the induction heater in combination with the capacitors is used as a workhead, and this coil has to be designed, manufactured in such a way that it must match the specifications of the work coil. And the work coil transfers energy to the workpiece, actually the metal element. The design of this coil is the most important part because this determines the energy transfer. And inductor design is always quite a crucial in most of the applications of power electronics, as we know. So this work coil is also one of the critical part. Yes. Then these induction heaters are used in industries, as we see in the last slides. And this is one of the major application which is used for non-contact type of heating. Even small induction plates might have seen at homes or your hostel rooms, etc., are very smaller application, or let us say the very small version of induction heating principle. Same principle, electromagnetic induction, have a coil, generate a heat, and pass it to the workpiece, means your metal object, means pot, so that the material inside, the food inside can be heated, food items can be. The same principle, but one is industrial scale application, another one is a domestic application. This is all about induction heaters and ballast we discussed in this lecture. In the next lecture, we'll discuss DC drives.